Welcome back, everyone. I'm Dr. Rhett Smith for ProtonGuru.com. Today we're continuing our discussion of organometallics and metal hydrides with lesson 5.2. And we're going to start by talking about how to prepare things called organolithium and Grignard reagents. Now, as the name suggests, an organolithium species is a species that has the organic group attached to lithium. Now, the pretty important thing here is the net reaction, where I can take an alkyl halide here, react it with lithium metal, and what you'll see is that the R group attaches to the lithium. That is our organolithium species. But remember, we have the R group and the X, so we're actually going to need to attach the X to lithium as well. So to balance the equation in the space that's left there, you can fill in a 2. So you'll need 2 lithium metal atoms for each molecule of the alkyl halide. Now, there are certain steps that go into this. This is not a concerted process. In introductory organic courses, you're not usually responsible for memorizing this or knowing this mechanism, but in case you are, it's provided here. Usually this is something discussed in more detail in an inorganic chemistry class. One thing you will notice is that you have the 2 lithium atoms, and they've each become a +1 lithium cation. So you increase the metal oxidation state by 2 overall, and you insert a metal by breaking the RX bond. R and X break apart. The lithium attaches to each side. Here we need 2 metals, not just 1, for this oxidative addition process to generate our organolithium species. Now, one really important safety note that's important even if you're just talking about this in class is that organolithium species are often pyrophoric, meaning they can spontaneously ignite in the air upon exposure to moisture and oxygen. So they can be extremely dangerous to handle without specialized training. Let's talk about another type of organometallic reagent. These are called Grignard reagents. This is another example where the metal inserts into the carbon halogen bond. In this case, the Grignard reagent always uses magnesium, and the halogen can be chlorine, bromine, or iodine, just like for the organolithium reagents. You'll notice this is another example of oxidative addition. And one thing that's nice about the Grignard reagents as compared to the organolithium reagents is that they're not quite as reactive as the organolithium. So they're a little safer to handle, although they're still extremely dangerous and require specialized training. One thing you'll notice here is that I specify that we have ether present as a solvent in this reaction. You will notice that none of the atoms from the ether end up in the product, but that ether solvent specifically is quite important for handling Grignard reagents effectively. That's because in the absence of an ether, Grignard reagents actually exist as an equilibrium mixture of multiple species due to that ligand exchange process we talked about. This particular equilibrium ligand exchange process is called the Schlenk equilibrium, and it consists of exchanging 2 R groups into 1 magnesium, 2 X groups into 1 magnesium, although the starting Grignard reagent itself started with 1 R and 1 X group. So what's the role of the ether solvent in this case? Well, the oxygen atoms of an ether solvent have lone pairs on the oxygen and a partial minus charge on the oxygen compared to the carbons to which they're attached. The metal, of course, in a Grignard reagent will be partially positively charged in this somewhat ionic bond between the magnesium, the R, and the X groups. So there's a natural attraction for them. So what you will see is that 2 ether molecules will coordinate to the magnesium, and once that happens, it actually shuts down the equilibrium process. So now instead of having a mixture of this, and this metal compound, which could mess up your reaction because now you have 3 different things in there, instead of that, you'll have one well-defined species, a Grignard reagent, which is the RMGX, coordinated to the ether solvent molecules. Now, although the organolithium and Grignard reagents are good sources of nucleophilic carbon, they're also strongly basic, and this can cause some problems in cases where acid-base and nucleophilic reactions can compete. For example, E2 versus SN2. That's something that's discussed a little bit more in your primer lessons associated with this video. But if we think about the Grignard reagent, which I'm kind of specifically talking about here, or the organolithium reagent that often does the same type of stuff, how could that act as a base? Well, if we think about the possibility for some ionic character to these compounds, and think about the R dissociating as R minus for the purpose of discussion, and then we think about how R minus would behave as a base, well, you can think of one specific example. Say it's just a simple methyl group. Think about how basic that will be. which is a stronger base? Hydroxide that we kind of learn as our first strong base we ever learn, or the CH3-? Well, in lesson 1.10, if you want to review, we talk about the influences of structure on the stability of anions. A minus charge on a more electronegative O makes it much more stable than a minus charge on a less electronegative carbon. That means that the methyl anion is much, much less stable than the hydroxide, and therefore is a much, much stronger base. This means if a methyl anion encounters an OH bond like you would encounter in water or in alcohol, you would envision a spontaneous deprotonation of that site to generate methane plus the minus charge on the oxygen now. Much more stable, therefore a spontaneous, thermodynamically favorable exergonic reaction. In the same fashion, if you can transfer the minus charge to a nitrogen to generate again methane and a minus charge on the N, well, nitrogen is also more electronegative than carbon, and therefore this would be a more stable anion. One thing you might notice is that we generate an alkane, and it's spontaneous, so it generates heat. This provides a mechanism by which these compounds can cause fires in the air. This means that if we try to use an organolithium or a Grignard reagent in the presence of anything that has an OH bond or an NH bond, we will have decomposition of these materials. What about the behavior of organolithium or Grignard reagents as nucleophiles? Well, we're going to apply the same sort of rules we did for figuring out if something was a good nucleophile or not in previous lesson. So if we consider that a nucleophile is generally a non-bulky anion, and we consider that our compounds in organolithium and Grignard reagents will often have a negative charge on a carbon, well, most of the organolithium compounds and Grignard reagents will then be good nucleophiles. So if my R group on an organolithium or on a Grignard reagent would be methyl, we treat that as a methyl anion when it comes off the metal, and that would be a good nucleophile. Now, on the other hand, if the R group was a tertiary butyl group so that it came off as this anion, that would be a little too bulky to be a good nucleophile and be a poor nucleophile. Well, what if we wanted to use some sort of organometallic reagent that didn't have this really strong basicity, right? These compounds are a little bit problematic because if you have any water around, or amines around, or alcohols around, Grignard reagents and organolithium reagents will react with those. If I need a source of a partial negative charge on a carbon to react with a compound that has these functional groups in it, we would need a different type of reagent. And this is where a compound known as Gilman reagents come into play. The Gilman reagent will always have the formula LiCuR2, so a lithium, a copper, and two R groups attached to the copper. And the way you make Gilman reagents is to actually take two equivalents of your organolithium reagent with whatever R group you're trying to transfer to the copper, and two of those R groups will attach to the copper then. You'll see that I have a butyl chain on the lithium, and now I have two butyl chains on the copper. The copper then will have a formal -1 charge. You can see it's copper +1 here, and you'll have to have a lithium counter cation for that. Now, usually the Gilman reagent's not written out like this. You might see it written out lithium, copper, and then maybe I'll use butyl as an abbreviation for the butyl chains too. Well, what happened to the other lithium? We had two of these, right? And we had an iodine here. So you also get some lithium iodide as a salt. Usually you choose a solvent where this will precipitate out, so it's easy to separate it away. Well, what do we do with these Gilman reagents once we make them? Well, one of the things we can do is to use this nucleophilic piece attached to the copper to replace a leaving group on this starting material. So, okay, if I did that, I would have these 3 carbons. Let me draw those out in blue. And I have these 4 carbons. Let's draw those in different color. And wherever the leaving group was, that's where the whole R group, the same carbon attached to the copper, will attach to that group. So you now have a 1, 2, 3, 4 carbons from the butyl group, and the 3 carbons from this propyl chain, 5, 6, 7. So you get this heptane from this. Now, why do I need the Gilman reagent to do that reaction when I have the organolithium reagent? Couldn't I just use the organolithium group directly? Well, if we try that and we draw out this instead of the Gilman reagent to react with the bromopropane, this is both a really strong base and a good nucleophile. So what happens is you have a mixture of the substitution and elimination processes. So it's not as clean a reaction. Another thing worth pointing out here is that mechanistically, The substitution of this leaving group for this R group by the Gilman reagent is not at all a simple SN2 reaction. It's not even a concerted process. It takes several steps. And one of the ways that you can examine this reaction to test whether it's an SN2 reaction or not is you could use the R isomer of 2-bromobutane. If this was a simple SN2 reaction, you would expect inversion, where this bromine would be replaced by this R group in the opposite configuration. What we actually observe with the Gilman reagent, if we use this chiral starting material though, is that this butyl group, which I'll abbreviate Bu, ends up attached in the same configuration as we had for the bromo. So it retains its configuration as you read about in the text. So certainly that is not an SN2 reaction, it's a more complicated process. In our next lesson, we'll talk about more of the types of reactions that both Gilman reagents and the other more reactive classes of organometallic reagents like organolithium and Grignard reagents can be used to accomplish.